So in 5.4, we get to start playing with logarithms. So we've kind of gone through this progression of what an inverse transformation is, what an exponential function is, and that the inverse of an exponential function is a logarithmic function. And we introduced this whole idea of language and graphing. Now what we're going to do is actually just do math with logs. So it's going to feel much more algebraic now. So there's 3 rules that you need to know when you're handling logarithms, which means there's only 3 things you can do with logs, which is actually kind of nice. The first one is called the product rule. So the product rule is that if you have the log base A of a product, so this is m times n, you can write it as the addition of 2 single logarithms, log to the base A of m plus log to the base A of n. So to prove to you that this is true, let's evaluate. So if I ask you what the value of log to the base 2 of 8 is, what would you think it was? So you're thinking 2 is the base. So 2 to what exponent is 8? It's 3. Well, 8 is 2 times 4. So I could write this as an addition of logarithms. Log to the base 2 of 2 plus log to the base 2 of 4. So I'm taking this multiplication in the of, and I'm switching it to an addition of 2 single logarithms. And so if I evaluated this, I would get that log to the base 2 of 2 is 2 to what exponent is 2 is 1, plus log to the base 2 of 4, which means 2 to what exponent is 4, which is 2. 1 plus 2 is 3. So it doesn't matter whether you evaluate it as log to the base 2 of 8 or log to the base 2 of 2 plus log to the base 2 of 4, you get 3. So now let's just practice doing that. So I want you to write these single logarithms as an addition or a sum of logarithms. So for the first one, we have a multiplication, 9 times 27. So this is a single logarithm, and what I'm going to do is I'm going to write it as the addition of 2 logarithms, log to the base 3 of something plus log to the base 3 of something. And the something is that you just take each of these numbers. So it's log to the base 3 of 9 plus log to the base 3 of 27. And then from here, you're going to evaluate if you can. So log to the base 3 of 9 is 3 to what exponent is 9, which is 2. Log to the base 3 of 27 means 3 to what exponent is 27, which is 3. And I could evaluate this as 5. So in your textbook, they often don't give you the chance to evaluate, but I wanted to practice a few that you do. This next one, you're not going to need to evaluate. So technically, this is expressing it as the addition of logarithms. But when you can evaluate, you should. So I want you to pause the video and I want you to write this single log as an addition or a sum of logarithms. Okay, so this is log base 10. So it's going to be log base 10 of 5, but we don't have to write the 10, plus log base 10 of g. All right, now let's go backwards. So we've expressed them as a sum of logarithms. Now we're going to take a sum of logarithms and write it as a single logarithm. So instead of having a log plus a log, we want to write it as the log of something. So this is going to be the log of 0.001 times 100, which I'm going to keep going. So this is going to be the log of 0.001 times 100 is actually 0.1. And then evaluate if you can. So this would be 10 to what exponent is 0.1, which is negative 1. So remember, 10 to what exponent is 0.1. If you remember that 0.1 is a tenth, then 10 to the negative 1 is a tenth. All right, so now I want you to take this next one and I want you to write it as a single logarithm. All right, so as addition, so this is going to be the log base 2. That's going to be my single logarithm of, you're going to multiply the up, so p cubed q. That's fine, or you could write it as log to the base 2 of qp cubed. It doesn't matter, right? So think of that commutative property of addition. They could be written in either order to begin with, or in here, they could be written in any order as well. P cubed q is the same as qp cubed. All right, second rule. The second rule is the logarithm of powers. And what it is that if you have an of, so this is the log base a of m, raised to an exponent p, so the whole of has to be raised to an exponent, then that exponent is allowed to multiply in front. So what it would be is log to the base 2 of 2 to the 3 would be the same as 3 log to the base 2 of 2. And so let's check it. Well, log to the base 2 of 2 cubed is log to the base 2 of 8. And then 2 to what exponent is 8? Oh, that's 3. If I check the right-hand side, this would be 3 times log to the base 2 of 2, which is 1. 3 times 1 is 3. All right, so now we're going to use this power rule to express these logarithms as products. So instead of as an exponent, so as a log of something to an exponent, we want to write it as the product of a number and a logarithm. So this first one, again, it's as simple as taking this exponent and just taking it down in front. So this would be negative 3 times log to the base a of 11. Done. Nothing more that I can do. What about this next one? Can you think of what the exponent on the 7 would be? So because there's a 4 in the index of a radical, you have to remember the rule that the index of a radical becomes the denominator of a rational exponent. So the index of your radical becomes the denominator of your rational exponent. And then you can use your power rule. So this is 7 to the quarter, so I'm going to bring the quarter and I'm going to bring it down in front. And this is going to be 1/4 times log to the base a of 7. All right, pause the video, try the last one. Is this a log? Well, ln, if you remember from the other day, is a natural logarithm. So this is log to the base e of x. We just don't write it as log to the base e very often. And so yes, you can use your power rule. This is just going to be 6 times the ln of x. And again, that's as far as you're going to go. All right, I'm just going to clean that up before we go to the next one. Sorry, my pen was just being a little bit funny. There we go. Okay, next one. This is your last rule. So the last rule is called the quotient rule. It's that if you have log to the base a of m divided by n, so this is your quotient, so you're taking the log of a quotient, and that is equal to the difference between two logarithms. So what does that mean? Well, it means that log to the base 2 of 8 divided by 2 is the same as log to the base 2 of 8 minus log to the base 2 of 2. Again, let's prove it. So log to the base 2 of 8 divided by 2 is really the same as log to the base 2 of 4. Log to the base 2 of 4, 2 to what exponent is 4? 2. If I was to evaluate this, I have log to the base 2 of 8, which is 3, minus log to the base 2 of 2, which is 1, and 3 minus 1 is 2. So again, the quotient rule is true. So now what we're going to do is what we were doing before. We're going to express these as a difference of logarithms, and then we're going to express a difference of logarithms as a single logarithm. So what about this first one? If I wanted to write this quotient, so the log of a quotient, as a difference, you'd have two logarithms. You'd have log to the base 3 of x, right, minus log to the base 3 of 9. I always think whatever's in the denominator is what gets subtracted. So this is log to the base 3 of x minus log to the base 3 of 9. And then evaluate if possible. So since we have a log to the base 3 of 9, now I can say that that is 2. And that is as far as I can go. All right, I want you to try this one, so pause your video. Okay, so for this one, you'd have log to the base t of 8 minus log to the base t of w. And because these are base t's, I can't evaluate, so that's done. All right, now let's go backwards. So to go backwards, what you're going to do is notice that this is log to the base b of 64 minus log to the base b of 16. So since it's a difference, I can combine them as a quotient. So this is going to be a single logarithm, log to the base b of 60, whoops, that's not a 64, that's a 16, of 64 divided by 16. And then you want to simplify if you can, and 64 divided by 16 is 4. This is log to the base b of 4, and that's as far as I can go. Pause the video, give the next one a go, answer as simplified as you can. Okay, so for this one, you'd have the ln of 15 over 3x. And then to simplify this, you have 15 over 3, which is 5 over x. All right, before I leave you, one thing that I didn't mention at the beginning is that logarithms are the inverse of an exponential function. Well, you know your exponent rules. your exponent rules are, let's start back here. When multiplying powers of the same base, you add the exponents. When multiplying logs of the same base, so let me say that differently. When you take the log of a base, when you take the log of a multiplication, it can equal the addition of the same base. I can't say it. I was trying to say it in the exact same words and it's not coming out of my mouth, but it's the same rule. When you're multiplying powers of the same base, you can add the exponents. When you're taking the log of a product, you can write it as an addition. So multiplication and addition go hand in hand. Okay, so this one can't really quite equate it to an exponent law, but what about, well, I guess you could say when you have a power raised to an exponent, you multiply. So that's how I could say that it ends up as a multiplication, as a product. But this one for sure, right? So division goes hand in hand with subtraction. Okay, all right, and that would be when multiplying powers, dividing powers the same base, you subtract the exponents. All right, give this first bit a practice, and we'll see you in a bit.